Okay, so I think I'm here because I'm part of a project called Petrus, which is looking at IoT and safety and security. I'll talk about Petrus more towards the end of this talk, but what I'm really looking at is trust and privacy and the challenges of what you guys are calling IoT systems, what I've always called embedded wireless sensor networks, wireless sensor actuator networks, and so on. Anyway, so the systems that I produce have been part of smart city systems now for some time. Back in 2010, we started talking with a number of interested parties and formed an institute to look at technology for smart cities. And the institute was sponsored by Intel, so it was the Intel Collaborative Research Institute in Collaborative Sustainable Cities. And we put both those words in because we wanted to look at mechanisms to allow the city to, make better use of its resources, but at the same time we kept the people in the loop. Now, my team are mostly the plumbers, so what I will concentrate on is not so much the human interaction, let's say. Okay. So we've seen from the last set of slides why on earth would computer scientists, for example, be interested in looking at cities, and why would city people come to us? Well, basically, it's a product of these two things here. Basically, resource optimization and smart decision making. So, for example, most cities are built around a particular set of resources, or they're bounded by the geography that they're in, and therefore they're not able to actually expand out to anything. So, if you can't expand out as growth increases, then you're going to have to do something about the resources that you have. And parallel to that was, if there are more people starting to join cities, which is the evidence that we're seeing now, then we can see that we have to make faster decisions so that we can keep all the mechanisms in that city to work well. And so IT at that time, this is in 2010, was considered one of the things, the oils that could keep that mechanism going. And of course, there was a trajectory at that time there. We were starting to see embedded systems and all sorts of things with smart televisions. We were starting to see how home IoT was starting to take off. And then we were starting to see a sort of trajectory towards where we could see these kinds of systems being embedded in everything from smart grid systems. You've seen this, the smart car, autonomous cars, and so on. So we saw this trajectory, and this was the sort of brave new world that we thought we were going to have. And at that time, myself and my team started to look at what are the big infrastructures in cities. Not necessarily, the above ground, let's say, the water infrastructure, the transport infrastructure, the things that if they fail, you could actually have civil unrest. So this is what we started to look at. And the big deal for us was that we wanted to retrofit these solutions to what was already there. Our water network's over 150 years old, so we have to think of solutions to retrofit to that. And at the same time, at other sides of the world, we were quite jealous of these big cities that were going to grow up from nothing and be smart from the start. And it's so much easier to embed all these systems in when you're designing the system, and you have your blue-green cycles and so on and so forth. And so it was interesting to see how we went and how many of those cities ended up in the end. So this is one of the Middle East smart cities that didn't really take off at all. Anyway, now there's a number of challenges when you start to shove IT in at the belt and braces end of the city. Asset management and those who own the assets are not willing to fork out lots and lots. They can't afford to fork out lots and lots of money just to get a new system in. So we have to look at what's called frugal computing. That is, computer systems that are low powered, low cost, and therefore you can get more of them out in that space. So the two things that we were looking at was low-cost sensing, that is low-cost processors with radio networks and reasonably decent sensors, and an alternative was to look at participatory sensing, which is to try and gather information from a space from people's mobile phones. The other thing that's a challenge for us was scale. In cities, even if it's a fairly small city, there's a number of, we have to look at the numbers of things in that space. And not only have we to be able to manage and make sure those little computers and so on are working, but the interact connections of those systems have to be maintained, and that's a very difficult challenge. And then finally, I'll come on to this in more detail later, but there's the capacity of a network to be able to support all these new devices is problematic. and it will actually determine whether or not we will see scale of these devices in cities or any large expanse that has lots and lots of computer systems within them. And then, of course, related to this particular workshop, trust is obviously paramount, and security and integrity of the data is core. And at the same time, we want to be able to have systems that we can't hack, that we can't bring down. You don't want to bring down a whole water network. Yeah, you would have civil unrest if you could do that. So you want unhackable, basically agile systems. Now, when we started looking at this, there was this vision of what a smart city would look like. And that was basically where you would have all these instrumented parts of the city feeding their data into this core, let's say, mission control system, where the seniors in the city would sit and stroke their beards and look at how they could make that city more efficient. We started from the very beginning to look at decentralization. And this is because all our lives we've been looking at the mathematical properties of anything that's dense or needs to scale. And decentralization is the only way that you can get a system to scale, adapt, and not be brought down by a single point of failure. So we started looking at it from a decentralized point of view. We also didn't want to have any notion of, the sort of systems that were, let's say, solution-based rather than, we had to engage our citizens. But in my case down at the Belt and Braces, we had to engage the water companies, the grid companies, and so on and so forth. So we wanted to look at how we could do that. And at the same time, we were starting to see a perfect storm, because the perfect storm was that technology was now being able to cope with this. So for example, we've got all these little sensor technologies. They're to be cost effective and to be able to scale, they are actually made of, let's say, they're made differently from your laptop. And as a result of that, they're not reliable, let's face it. The clocks drift seconds a day, they can fall over if the temperature changes, and so on and so forth. And this is typically, the expectations of a laptop has been projected onto these tiny little systems. They're not the same computer at all. Now here's the problem. So we've got these inherently unreliable technologies, which are the basis of a lot of these city systems. We build the agile protocols, that is algorithms and communications protocols that assume the system is unreliable and makes the best system out of what it has. So it'll do things like if somebody kicks one of the little computers out of the way, it won't bring the whole network down a route past that. So we've got all these algorithms built in for resistance. However, here's the perfect horrible storm. The trouble is, by building these systems to be agile and resilient, they're actually more hackable as a result. Okay? Because they're trying to understand their environment, they're trying to be agile, so they're gathering information from their environment, they're doing their job, and they're trying to make the best of what they're doing. And in doing so, they can be easily misled. Okay? That, combined with the fact that they're unreliable, low-powered, low-cost systems, means that you can't put your sophisticated security algorithms and your protection algorithms that you have even on your mobile phone onto these systems. So we've got this perfect storm which we need to cope with. So security is obviously a big deal in these kinds of systems. As I said before, we have resource-constrained nodes, therefore we can't put heavy analysis on those nodes. We can't have a notion of centrally controlled nodes because that would be central points of failure. We've got a notion of self-organisation, and then how do you make guarantees a system will conform to what it's supposed to do if it's self-organising. If it's a system of systems situation where one system is organising to maximise its own opportunity, how can we guarantee that the other one doesn't steal that opportunity, and so on. So there's a lot of things to look at, so it's not really the same kind of system as we have before. And it's broken. Right, what do we not see here? Oh. So talking of unreliability.
That's us, not you.
Listen.
Let's see. I think what's next is probably a slide that has a video on it, and it doesn't like it.
Has it blown up? And the IT guy should be in.
Do you want me to cancel and then start again? If I just know what my next slide is, then. Anyway, So what we've been doing has been looking at that. We don't take that to all lying down. So we've been looking at nice ways and clever ways to make sure that these systems will be as secure and reliable. It's that trade-off. I think the one thing I want you to go away with is if you want a safe system, it has to be both resilient and at the same time safe. And the two things in IoT, unfortunately, are against each other. And that's the problem. So how do we do that? So to be honest, the algorithms we tend to build have a notion of like a slider. So you can slide up the reliability or you can slide up the safety, and you lose in some other way. And that's the kind of way we've been looking at it. You can ask questions now if you like. Yeah, and down.
There was a video to go and
Yeah, oops, where were we?
We will get it.
Up, back. I think it was the DDoS, was it? It was coming next. Oh no, so I don't know why I died on that. Okay, that's
Right.
a nice slide. Okay, so this is just an outline of the kinds of attacks that you'll see. Is you going to pick up? I'll do it. Oh, it's just slow for some reason. Okay. I'll do these all in one go. Okay, so these are an idea of if you break down the kind of layers inside an IoT system, there's all different sorts. So the physical layer, you've got the communications layers, transport and so on up to the application, and then from there it's the services layer onwards. And there's different, for each one of those layers you'll see that there's different types of attacks that can happen. And they're not necessarily the same. So for example, a jamming attack is somebody who's purposefully put a computer system, it could be a tiny little computer system you can buy for 25 quid, like a TI tag or something, and you can put a radio system on that will just jam all the signals. And therefore, your water network will not be able to communicate at the state back to where it's supposed to. So those kinds of things. Also, we can eavesdrop over them if people are sending non-encrypted data. And encryption is very expensive on these systems. You have to remember some of these little systems can't even do floating point arithmetic, never mind an encryption algorithm. So these people have not realized that these could be eavesdropped upon as well. The other thing is you could have purposeful collusion where you've got a bunch of nodes in the system are actually colluding to subtly distract the actual real system and therefore either elicit data from it or make it fail in some way. And then other sorts, for example, are malicious code or malicious data attacks. A malicious data attack is basically twofold. One is where the system itself is grabbing the data from your IoT system and changing it in some way and reporting that back. So it's a man in the middle, as it's called. Then you get information back. You think it's coming from your system, and in fact it's not. It's coming from another node. Or you could have a situation where, for example, the data, as I said before, the system itself trying to keep itself alive and trying to keep itself resilient is listening to all of the other systems in the environment and mapping its way around that. If it gets false data to do that, it could be constantly trying to map its way around and not send the data at all. And therefore you've got a false data injection on the control part of that system. And it can also put other false data in as well. So we've been looking at a lot of these attacks. And one of them, and hopefully this will run, if it doesn't, it's not a big deal. I'll let you see how it happens. So what we were looking at initially was we were talking about resilience. I don't think it's going to run. I don't care. It doesn't matter. And as I told you before, these systems fall over a lot, as do laptops. And if they fall over, we want to understand that the data we're getting in is trustworthy. So we have this notion of a metric that measures the trustworthiness of a piece of data. And that metric is a product of many things. So for example, sensors can be decalibrated. And they do decalibrate regularly. So if you look at the V&A Museum, for example, it's got 800 node sensor system in it. And they recalibrate 40 sensors a month in that. They have a turnover of 40 sensors a month to be recalibrated and re-battery powered. On the subject of battery powers, when the battery power goes down, depending on the type of sensor or the sensor node, the battery or the sensor could be providing data that's not actually the truth of the phenomenon, and so on and so forth. So we have to understand whether or not we're seeing decalibration in the data or any other falsities, or that just something has happened in the transfer of that data back to where you need it. So we were looking at that, and we had built a bunch of algorithms to look at that. And what we found is that we could also, with the very same algorithms, detect when someone had put false data into the system. And what I was going to show you there was showing us running that very same algorithm over a smart grid network. There's a smart grid benchmark system that allows you to show how data, they inject the false data into it, and it allows you to test whether your algorithm can pick up that false data, and ours actually did as well. So we were able to show not only unusual data due to something going wrong in the computer system, but where it's malicious and actually purposefully gone wrong in the system. We also showed this, and at the same time, when there is a genuine anomaly, that it would still work. I want to get on, and it's not letting me. Okay, let's go to it. This is not good. I do have a machine now that will run it. It won't even escape. It's dead.
I'll get the IT guy.
Or can I, what is it? Is it just a normal plug? I can plug my own in. Sorry, it's going to take longer. Anyway, the other thing I wanted to say was there's that. The other things I wanted to say is, so we're looking at that. The other thing is, right, so I, like our previous speakers, also believe that data should be owned by the data source, okay? And the data source should sell that or provide it in the way that they want to those who make money for it, right? And so to do that in an easy way where all people win, including those who do the data analytics offline, I call it off on the data servers and so on, we have to look at algorithms that allow us to do that. So we've been looking at algorithms that obscure the data from the data source, to, again, like a slider, to the degree which the user, the owner, wants. And then at the same time, we've mathematically proven that data has enough richness of information in it that it will provide enough information for data analytics. And so this is a whole field of study right now where we can have almost the best of both worlds. So if you want your data to be super private, it loses some of the information on the back end analytics, or if you want it to be more loosely private, where you can maybe ascertain maybe the region where you live but not you individually, then we get much better analytics and much richer information for our offline analytics. So this is a whole nice piece of research that's going on at the minute to allow the best of both worlds. I think I'll probably be going into conclusion soon because I'm sure our 20 minutes is up.
It's 3 now.
Right.
You have a couple of minutes. So,
Yeah. Okay, and then finally I wanted to mention 2 projects. Now here's the thing that might make you a bit squirmy. All that I've been talking about. Now if you look at normal computer systems, we have a notion of the science behind those, right? We understand how computation works to a certain degree, right? And we have done since the 50s. You all know Turing. Anyway, okay. So we have mechanisms to allow us to verify and ensure to certain levels that the system will not misbehave, it will do as it's told. However, these little systems, because they're flaky and because they're physically placed in the environment and the environment impacts on them and they impact on the environment, are not of that class. I'll give you an example. We have a water network instrumented. The water network is basically 2 networks. You've got the water network, you've got the computer network. We have to optimize the water network for water demand and to also detect leaks and also to keep the system working over time so we can't have weird transients that will decay the pipes. It's the water network. Computer network on top. Computer network wants to last at least 10 years. It wants to provide accurate data and it wants to do it as fast and as cheaply as possible over the communication network. So I'm optimizing this network, and here's where it gets even more complicated. This network, the water network, is providing the power to this network because it's running on harvested energy. So this network is basically, as it pumps water through it, it provides energy to this one. Now, if the energy is not good to this one, it lies to this one. Okay? So we've got this super complex system. We don't have a science for that right now. Okay? But don't worry, rest assured, the EPSRC have given us lots of money to do that very thing. So we're looking at that. And the other thing is, obviously, the Petrus project, which is, I think, why I was brought here today. Petrus, I think it was a £10 million project from EPSRC as well. Lovely project. Everybody's looking at the security of these kinds of systems from my side, which is the sort of belt and braces plumbing side, to the policy side, human behaviour side, because let's face it, the DOS attack that you would have seen on the screen there was human error from passwords and so on and so forth. So as a sort of collection of people, we're getting together and looking at the interactions of all of those, human error versus my kinds of systems errors and so on, to try and sort this out once and for all. And I think I'll leave it there.